In this video, we will examine the free body diagram and equilibrium of pin joints by using the free body diagram module in the statics power software from Actus Potentia. We will see that in some situations, the equilibrium of pin joints lead to the statement of Newton's third law that action equals opposite reaction, and in few situations that we will identify where you need to draw the free body diagram of certain pin joints, and in those situations the equilibrium of the pin joint is not only a statement of Newton's third law but something more than that. So let's start with a simple A-frame which consists of three members. We will connect the members with pin joints, add a pin support at A and add a roller support, and then we will add some loading on this member. Let's say we have a point force at a distance of 5 with a magnitude of 1000, and on this member we will put a couple at a distance of 5, the magnitude of 2000. Remember that these magnitude and locations are unimportant as we are paying attention to the underlying principle only. Now if I draw the free body diagram for this case, so here is the two forces coming from the pin support. Here is the force coming from the roller support. We will look at this pin at node B, which connects two members. If you look at the free body diagram of member ABE or CBD, then you will see at node B we have a pair of two perpendicular forces which are denoted by 0bx and 0by. If you look at member CBD, then again we have a pair of two perpendicular components, and this is denoted by 1bx and 1by. So we have 0bx, 0by, and we have 1bx, 1by. If I look at the free body diagram of pin B, what we see is 1bx and 0bx, they have the same magnitude but they are opposite, which is consistent with the Newton's third law. And on this direction we have two forces, 0by and 1by. They have the same magnitude but they have opposite directions consistent with the Newton's third law. So effectively it means that at a pin, when two members are joined, the equilibrium equation for that pin is just a statement of Newton's third law, that is, action equals opposite reactions. Now let's make a modification to this structure. We apply a force at pin B of magnitude, let's say 3000. Now let's see what happens to the free body diagram of pin B. Now what pin B would do is that external applied force shown with this green arrow will be divided among the two members that join at the two members AEB and BDC that come together at pin B. So let's draw the free body diagram. Now what we have is just as before, 0bx and 0by. Member CBD has 1bx and 1by. But just because we have an external force, the 0bx and 1bx, they are no longer equal and opposite. So let's look at, so now you see pin B. Here is the external force, 3000. And now if you look at 1bx and 0bx, they are no longer equal and opposite. They're opposite all right, but they are not equal. However, on this direction, the 0by and 1by are equal and opposite. So just because this force is applied in the x direction, the Newton's law seems to be violated, but that is not the case. What is happening is that this 3000 unit of horizontal force is getting partitioned between 1bx and 0bx, and you can see that if you look at the magnitude of 1bx and 0bx, there is a difference of 3000. So in the x direction, it's no longer a straightforward application of Newton's third law. Situations like this, I call situations like this, is that there are special pins where more than two things are happening. So at node B or pin B, the more than two things happening. That is, there is a member, a second member, and the third item is a horizontal force. Now let's look at another situation of this type. So now we build an A-frame which again consists of three members, but let's put the third member, instead of putting it horizontal connected somewhere in the middle of AB to somewhere in the middle of that member, we take it there and connect it here, and then connect them with the pin joints. And then we take a pin support, put it here, and take a roller support. Then we apply the loading on this. Let's put a point force at a distance of 5 with a magnitude of 1000, and on this member let's put a couple at a distance of 5 with a magnitude of 2000. So now this is our structure. So now look at pin A. At pin A, more than two things are happening. What are those things? Member AD, member AB, and a support. So when more than two things are happening at pin A, then the equilibrium of pin A is no longer a simple statement of action equals negative reaction coming from Newton's third law, but it's more than that. So let's look at the equilibrium of member AB. We have 0AX and 0AY as before. Let's look at member DA, and here we have a F2A which is coming from the two-force member. Now if I look at the equilibrium of pin A, what do we see? We see 0AX coming from member AB, 0AY coming from member AB. In addition, we have a AX which is coming from the support. We have a AY which is coming from the support and the F2A which is coming from member DA. So you will notice that at this point, at this pin, it's not a simple statement of Newton's third law, but way more than that. There are three things that are happening at this point. One is 0AX, 0AY coming from member AB, AX and AY coming from the pin support, and on top of that F2A which is coming from member DA. In this situation you will have to draw the free body diagram of pin A. Why? Because at pin A more than two things are happening. There is a member AB, thing number one, member AD, thing number two, and AY, AX, which are coming from the support. That is thing number three. Thing number one, AB, thing number two, AD, and AX-AY pair, which is coming from the support. So what is the takeaway from this video? That is, when you are looking at a frame, examine each and every pin joint. If a pin joint is connecting only two members, or a member and a roller, or a member and a pin, then the equilibrium of that pin is a simple statement of Newton's third law, and you can, in most cases, you can even ignore it. But when more than two things are happening at a pin, like in here, you will have to draw the free body diagram of the pin. This concludes this video.